Thank you all for coming to this, the fourth in our science seminar series, which we're running every 6 weeks or so to try and get the word out there of who we are and what we do. And I mean, the goal really is to put ourselves out to the wider organization. It looks like most of us are actually still from the science group. Something we might still need to work on a bit, but there's a few people here that are from outside the group. And even so, obviously not all of you are in the groundwater section, so you'll be interested to hear what Lisa has to say. So today we welcome Lisa Scott, Dr. Lisa Scott, who has been with us for 4.5 years now. She's got her PhD in geochemistry from the University of Cape Town in South Africa, and she also did some postdoc work in Eastern Canada, in New Brunswick, and she's been with us here 4.5 years as a groundwater quality scientist. And Lisa today is going to tell us where groundwater comes from. Thank you, Lisa.
Hi, thank you, Carl. Yeah, sorry, my talking heads were supposed to be blasting a whole lot louder so that you could hear about water flowing underground and wake yourselves up if you were too late watching cricket last night, like I was. All right. So when this went up on the bulletin board, Fleet, everyone knows Fleet, came rushing over to me in the tea room and said, "So, where does our groundwater come from?" And he took me completely surprised, and I sort of said, "Well," and Len thought that was the funniest thing ever. So, I don't really know how to answer this question. Carl came up with this question, and I started with a really big picture, like, where does all the water come from? Because groundwater is part of all the water on the planet. We've got one of the wettest planets that we know of, and it was just part of that. And so I started looking into where do people think Earth's water came from? And nobody knows. It's quite cool. They still don't know. I mean, there's some ideas that it was part of the planet and it outgassed along the way. There's a really interesting geo group who talk about all these hydrated minerals. You know, like gypsum has water in the mineral crystal, and when you heat it up, it becomes anhydrite and the water comes off. They think that these hydrated minerals are all down there in the primary water river system, and they're leaking all this water up, and then it gets trapped. And you can find that if you go with your forked sticks and find where this water's got trapped. It's leaking from the primary water system. There's a bunch of people in Japan who think that there might have been a whole lot of hydrogen around in the Earth's atmosphere, and that reacted with oxide minerals and made water on the planet. So those ones don't really have a whole lot of credibility. Other places that water could have come from, volcanoes, gassing on steam and forming the water on the Earth. There were a lot more volcanoes in the history of the Earth than there are active today. Maybe it came from biology. Biochemical reactions synthesizing hydrogen and oxygen, but some people say that they use up as much water as they create, so they can never be responsible for all that huge amount of water that's on the surface of the planet. The most popular one is that they came from outer space. That the young Earth was too hot to hold on to its water, so whatever was there disappeared, and then all these comets and asteroids that collided with the Earth brought water with them. They're starting to argue against the comets because they're finding out more about comets, and it's got the wrong type of water on most of the comets they've tested, like that one that Rosetta landed on. There's got too much deuterium, or the heavier isotope in water, and so it doesn't look like our water. So now they're talking carbonaceous chondrites is where water came from. But anyway, jury's still out on where water comes from on our Earth, but about 70% of the surface is covered with it. And most of that's saline. Oh, sorry, I'm standing for my slides. Knew I was going to do that first one. So a lot of it in the oceans, a little bit of fresh water. This is how much of our Earth is solid, and that's how much of it is water in a relative scale. So that's all the saline water. This is all the fresh water that's on the top there. And about 1/3 of the fresh water is present underground in the groundwater. And it all goes round and round in this nice big cycle that everybody learned about in primary school, driven by the heat of the sun and water evaporating out to oceans, condensing and precipitating as snow, rain, and falling on the ground and running off in streams and lakes and getting into the groundwater by infiltration from the rain, from the rivers and from the lakes, and that's what's filling up this groundwater reservoir. So when I'm going to look at this question of where did groundwater come from, I think I'm going to try and narrow it down, because I can't answer the big questions. I'm going to try and answer some of the smaller, narrowed down questions about where does it come from, how does it get into the ground, where are the connections. So we're looking at where do we see rainfall recharging our aquifers, where do we see river gravels leaking water from rivers into systems into our aquifers. So this one's just another pretty picture to say exactly the same thing, but the two main sources of what we call recharge to groundwater are water that infiltrates through the soil, so it either falls on the surface as rain, or this one's got a little sprinkler on top of a lysimeter. And the lysimeter is a core of ground that's dug out, and it's used to measure how much water is draining through the soil. And so that's one form that we call land surface recharge, rain and irrigation water draining through the soil down into the water table. The other one is the big one, is our rivers. Rivers flowing across permeable gravels lose a lot of their water. We see that quite often in Canterbury because the riverbeds are so permeable. And think of examples like the Air River, the Selwyn River, all those rivers that don't quite make it to the coast because they lose water along the way to groundwater. And the big alpine rivers do it too. They don't run out of water, but they all lose to groundwater. And so here we have the water table, the groundwater table at lower levels than the water in the river, and the water draining out of the bed of the river and feeding the groundwater. So how do we find out where these connections are? Like, how do we do this in space? How do we know where the groundwater is coming from if we go to a particular part of our region? And there are two things I want to talk about that we use to find out where it's coming from. The one is flow lines, and I'm going to talk a little bit about flow lines because flow lines is what all the hydrogeologists do, and that's a little bit out of what I really like to talk about, which is the chemistry. And so unfortunately you're going to be bombarded with lots of stuff on the chemistry and the traces, which is the next one. So flow lines, contribute to the Terry Pratchett flows are driven by gravity. Water flows downhill, and we see that in our rivers, but it carries on flowing downhill when the bottom of the river is not going to impede it flowing down, but it can go further down than we think. So if you talk about flow lines, some people think of this method of finding flow lines. You've got to feel the energy. The Geo group on the internet has a lovely website where you find that primary water by feeling the energy, and it feels slow, warm and fuzzy, or like chocolate syrup, and you follow the flow lines, and heaven forbid if one of those flow lines goes under your desk, because that's probably why you're feeling lethargic at work. You better move your desk off the flow lines. So we find flow lines a little bit differently in the groundwater section. It's probably a bit more boring way of finding them. This is Carl demonstrating our equipment, which is I feel like we call it a prodder. I always called it a dip meter. Anyway, it's a tape measure with an electrical connection at the bottom that you lower down the well, and when it hits the water, it completes the circuit, and the needle swings, or the buzzer goes, or the light comes on, or something, and you measure on the tape how deep it is to the water table, and then you make a map of where the water table is. So these are all your wells plotted on a map. You correct it to, this is probably a little too simple for all the scientists in the room, but anyway, you make a map of the height above sea level of where the water table is sitting, and then you do some interpolation and contouring so that you can draw these equipotential lines where the water table is at the same height, or at least at the same pressure. And then because it's driven by gravity and pressure, the water goes downhill, so it goes from a high line to a lower line, and it follows these arrows perpendicular, and you can make nice maps of groundwater flow. Sorry. And this is one showing the flow lines for Christchurch. So there was a mesometric survey. I think most of this data comes from measurements that were all taken over 3 days in 1989. And they measured the water table in a whole bunch of wells in a very short period of time, plotted up all these contours and where the water table is, And if you take lines perpendicular, you can see some of the water goes north and some of the water goes a bit south. And somewhere down here there's a divide where it goes this side of Banks Peninsula. It's not an absolute science, we can't draw a line on the ground of where that divide is, but we can get a good idea about which general direction things are flowing. And I've drawn these blue lines here because I've tried to put some of our monitoring well networks along the flow lines so that we can see how water chemistry is changing down flow paths. Just another example I stole from Vicky and Philippa, some South Canterbury. These are metric contours, so contours of the water level, and then the little black arrows showing where the flow is, mostly down the river valleys where these alluvial sediments are, and flowing into another lagoon there. This is my last example. You can make it quite complicated if you want to. They certainly did on this Ashburton survey from 2010. They did well water levels from 3 different depths, and so they've got 3 different sets of contours with different flow patterns on that map. And so where's the groundwater coming from? It's coming from up gradient. It's coming from going down the line. Follow it back. Traces. We get to the chemistry part. So groundwater dissolves stuff, and we can use the dissolved stuff to tell us a bit about where it came from. There's 2 types of traces. There's artificial traces. Those are ones that we put in the ground. Usually some sort of experiment where you inject something down a well, and they've tried all sorts of things. Most of these have been tried in Canterbury. Dyes, rhodamine dyes, particulars that dye. Salts, they like to use bromide, potassium bromide, because it's very soluble and it moves with the water, but it's also not naturally present at very high concentrations, so you can pick it up as a signal when you're testing for it in other wells down gradient. Bacteria, they did quite a few bacteria-based tracer tests at Templeton and Burnham several years ago. Some of them, I think they tried to use less harmful bacteria to figure out where more harmful bacteria might go. And Leaping Pang at ESR has been working on using little beads, latex beads, to simulate viruses and see how those move in groundwater. So various ways to. But the problem with artificial traces is you need an awful lot of tracer to pick it up before you're measuring, because there's a lot of groundwater, especially in big alluvial aquifers, and a lot of dilution. So they're usually quite specific, small-scale experiments that you have to do with a tracer. You couldn't just put in a huge whack of tracer at the top of the Canterbury Plains and figure out where it had gone to. And that's the beauty of the natural traces. It's things that the Earth has put into the groundwater for us, and we can use those to figure a bit more about where it comes from on a catchment or a regional scale. So, some pretty pictures. Adrian said put lots of pictures. Some pretty pictures. Oh, this one's a little bit of a fuzzy picture, sorry. That's from Rod Dan's paper, but it's pretty much just illustrating this Burnham site where they've done all the tracer tests with the bacteria, but they've also used this is the results for a rhodamine, so that pink dye tracer test, and they put it in this well up here, and all these blue dots are arrays of quite closely spaced wells. That scale is only 60 metres, and they've measured where the concentration over time in each of these other wells and figured out where it broke through. And they found it didn't just flow in a nice straight line, because it was following these highly permeable channels underground, kind of like, braided river channels, but they've stacked up into an aquifer. And so the groundwater flow system on this very local scale, where this groundwater came from, it came down this particular channel. Okay. And then I said you can't usually put in enough tracer to see it very far, but some very kind meat work processing people have put in a quite big block of nitrate tracer for us just near Ashburton. They've been discharging wastewater for quite a long time in that area, and when Carl and Shirley, I think, sampled a whole bunch of wells, you can see where that groundwater came from. So we've gone down the red shading is mine, but the little red dots were all where the nitrate concentration was high, and it's followed the flow path of the groundwater. All right, so those were all artificial traces. Now we get to natural traces, and I can't believe this is what the fourth science seminar, and this is the first time the periodic table has appeared. Periodic table of elements. And the point with this was not to get into the detailed chemistry of anything, but to remind myself that rocks are made of minerals, minerals are made of chemical elements, and those chemical elements, even though we think rocks don't dissolve, if you put them in groundwater, leave them there for a very long time, things start going into solution. I said you get mineral water. And so we use all those chemical elements dissolved in water to tell us a bit more about where the groundwater is coming from. So most rocks are made out of silicate, especially the grey gravels around here. And they tend to contain some cations, sodium, magnesium, calcium, potassium are the four that we look at quite often, and some anions, which are usually some of these elements, chloride, sulfate, carbon, combined with oxygen to bicarbonate, sulfate, and sometimes a few other things like some metals. But so most rocks contain some of these and some of these, and then different types of rocks contain different minerals. So say the water that goes through a limestone is going to pick up a very different chemistry from the water that goes through a silicate gravel. So, and you can see it in the chemical analysis, and you can taste it in the water that it's picked up some different chemistry along the way. So the one thing you can do by looking at the chemistry of the water is figure out if it came from a different rock. But the other thing you can do is also figure out how long it's been in the rock. Even if it came from the same rock, it can tell you something about how long it's been in contact, because those compositions change slightly over time. Some things are more soluble than others, and they slowly go in and out of solution. And there's other processes like ion exchange. So you get evolution of your groundwater composition along the flow path. And in Canterbury, we usually start with water that drains through from rain, comes out with calcium and bicarbonate as your main ions in the water, and then it can follow this pathway. It starts exchanging and going down towards a sodium bicarbonate, but mostly we don't get very far along this, and there's two reasons. One is our rocks don't react very much, so they're not very helpful in that regard, and the other reason is that our groundwater doesn't spend as long underground as it does in some of the other aquifers in the world, which is moves too fast to get a nice big. So we don't see a whole lot of this like saline sodium chloride brine, or even the calcium chloride brines right at the end of that sequence. But we do see a little bit of evolution in our groundwater. And so it can tell us a little bit about, is this sample younger or older, even if we don't have fancy things like age traces. Okay, brace yourself for Piper diagrams. Okay, they look a bit scary, but hopefully I'll be able to explain my way through them. We're trying to put the whole chemistry of the sample into something so you can see it all at once. So instead of giving us a whole list of concentrations, what I've done here is use these diagrams, put all the cations in this triangle, and I've just worked out percentages, so proportions of each. So something in this, near this corner's got more calcium than anything else, near this corner's got more sodium than anything else in the cations, and near this corner's got more magnesium. And the same thing on the side of the anions, so more carbonate, more chloride, more sulfate. And then you take one dot here for your sample anions, one dot there for the cations, and you extrapolate up into the diamond and you put a dot there. And that's how you can follow these diagrams. But basically, they show you patterns of if lots of dots plot near each other, the water probably comes from the same kind of rock, and it probably comes from a similar age. If the dots plot further apart, the water might come from a different kind of rock, or it might be more evolved. And so it tends to follow a line across. And that's probably enough of that. I could go on for ages. Alright, so here is just an example of how that works quite neatly in Christchurch groundwater. I pulled some data out of a database for a bunch of wells near McLean's Island, and they're all calcium rich and they're all bicarbonate rich. They look like fresh recharge water quite over there. Then I found, I had to look for it, some data that was collected from springs in Banks Peninsula. And they have more chloride and less sulfate, and they plot like that. And so those are the springs that come from volcanic rocks, so they have a chemistry, and that little diagram tells me that those two types of water come from different rocks. I used this when I was doing some work on some sampling we did in the Waitaki Valley, so I had my hyper diagram telling me that this pink sample, which you can hardly see, but it came from a well up here, which is in the Kauai Formation, the Cannington Gravels, had different chemistry, so it's like, oh cool, why that groundwater doesn't match. There's one over there that you can't see at all, but comes from the Murrowhenua Basin, and that came from a different kind of rock that had some sulfate in from the Taratu Formation. And then the other rocks sort of followed a pattern of the groundwater, either mixing or evolving. And combining all the chemistry data and some of the isotope stuff that I'm going to talk about later, I can come up with a system that can tell me almost every single well what was the dominant source of groundwater. So the ones with the blue arrows are the wells where river recharge is mainly where that water is coming from. The ones with the yellow arrows are the ones that's mainly drained through the soil. And there was even one where I could see that it was river water irrigated onto the soil, just because of the way the chemical patterns are. So small area, but quite a complex set of influences on where the groundwater is coming from. We make it a bit simpler. I mean, those triangle diagrams are a bit of a nightmare for people who don't play with them all the time. So this is just taking two ions, calcium and magnesium, and taking the ratio. And that actually gives you a whole lot of information. Sorry, I don't know where my scale went to, but calcium over magnesium is quite high in our alpine rivers. There's hardly any magnesium in them, so they come up with these purple dots. And all the groundwater that's being recharged from the Rangitata River has the same signature. And then on this side we have the Orari River, which is coming up with quite a high calcium-magnesium ratio. And then the soil drainage, the land surface recharge on the plains in between looks quite different because it's all quite much more magnesium in the lower ratio. And so you can sort of map out, gone too far. Those groundwater came from 3 different places. Even simpler still, this is just a map of conductivity. So measuring the specific conductance of the water. One measurement tells you something about how much dissolved salts are in it, and that tells you that this groundwater comes from somewhere different from this groundwater down here, and thankfully different from the Burwood landfill as well. Okay, now I'm going to be brave and talk about oxygen isotopes, and hopefully I'll make it simple enough to understand. But this is a science seminar, and I'm going to look sciencey by putting in an equation. You've got to have an equation. So the equation is just how we measure oxygen isotope ratios. What that is a little bit of basics. This is your oxygen item that you learned about at school, 16 is its molar mass, but in nature there's also a little bit of more heavy oxygen. It's got a couple of extra neutrons in the nucleus, if anyone remembers that part of science. There's a nucleus in the middle of the atom. And so its chemistry is the same, but it's got it's slightly heavier. And so physically it behaves a little differently. It evaporates more slowly and it condenses more readily than the normal oxygen 16. But there's only a very little bit of this around, so to measure it you get a really, really low concentration, and that's why you need this fancy formula, because you work it out as a ratio of the normal, what I call the normal oxygen 16. And you standardize that to seawater, which has a fixed amount of those two. And so the point is that this tells us where the water comes from. It's very cool. This ratio, the delta 18O, in the ocean is set at 0. And then when it evaporates, more of the light ones go in and you get a negative number. So you get a negative 018. Some of it precipitates out and loses some of the heavy, but it carries on through the cycle. And as you move further and further away from the ocean, you get more and more negative numbers. And as you move higher up and colder, you get more and more negative numbers. And so the rain falling, at the top of the plains is very negative, 18, minus 10, minus 11, minus 12. And the rain falling near the coast has less negative, minus 5, 6, 7. And the rivers that come from this rain also have that same number, because it doesn't change that much once it's fallen as rain. And when it grows into groundwater, it still doesn't change. So it pretty much keeps a memory of where the groundwater came from. And I looked at, last year I compiled a review of all this data, because we have about 2,000 odd samples of groundwater where we made this measurement in Canterbury. And I compiled it all into a review, and I came up with a scheme that we could pretty much classify whether something was from coastal rainfall recharge to alpine river recharge, which is kind of heading down into the -9s, -10s, and then our high country basins have the most negative OAT. And if you can try and remember this kind of colour scale, so the less negative is red and the more negative is blue, and I've tried to use the same scale in some of the maps that I'm going to show. So, I told you there were lots and lots of samples we'd taken in Canterbury. There's one dot for every well where we've sampled O18, and the triangles are springs. And we've got a lot of data, and it looks a bit of a mess, but if you pull it apart, it starts telling really interesting stories. These are all wells where the groundwater has an average OAT identical to the long-term mean of the river that's next to that well. So these wells look like they're recharged by the Ashley River, the Mamakuru River, the Kai River, Rangitata, Orari, and something in Ashburn. Match exactly. There's a lot of other wells that also have alpine river signatures, so you start thinking, well, maybe it's not that useful. Some of them are a little bit further away from the river signature, and they might be mixed with something else, but they're all pretty negative OAT. And you think, well, they're probably coming from the rivers. Those ones that are in the river alluvium definitely look like they're coming from the rivers. But there's also all these ones on the plains. So where is that coming from? And then I've got on the irrigation schemes where they've been pouring a specialist border dike from the Rangitata River, alpine river water, onto the ground surface for decades, and there it is. That's where it's coming from. That's where your groundwater dominant. It's also groundwater there. It's probably alpine river irrigation. And so these are the same oxygen isotope measurements for that area of the Rangitata Orari catchment that I showed you earlier. And I just wanted to show you this because it was quite neat. I've got two different traces and being controlled by two different mechanisms, and they're both telling me the same thing. This is Rangitata River water, that's Orari River water, and everything in between is lands of this recharge. The other side of the Orari, is the Orari River loses a lot of its water to groundwater, and it all seems to flow mainly. There wasn't that much on this side of the river, but there quite a bit of it seems to be losing to the south, and all these spring-fed streams down here, their oxygen isotope signatures don't look anything like the rain that falls in that area. They don't seem to be coming from the rain at all. They're coming from the Orari River water that's coming out in a Harvey Creek. I can read those names, or in the other little spring-fed drains down there. But the upper Waihi looks like it's coming from hill-fed rainwater. So we know that the groundwater here is coming from that river, and it's coming into the spring-fed streams. It even works in Kaikoura, the Kowhai River has quite a negative OAT, and all the wells that are in its alluvial plain, alluvial fan, have a similar signature. They look like they're getting lots of river water. And the ones on the plains where it's older sediments all look like coastal rains are very less negative. I just mentioned coastal rain being less negative. The rain signature, we don't have a lot of rainfall data for these. We have a lot of groundwater data, but nobody's measured these measurements in rain because they're so up and down that you take a really, really long-term average to get a good signature, whereas groundwater seems to be quite constant over time. But where there is data, it does follow this pattern of being less negative at the coast. Less negative at the coast and much more negative at validate some of our theories. And so I also made a map of where all the wells on the plains are mainly recharged by lowland rainfall. And that's pretty much fits in with areas that are outside big irrigation schemes and away from the rivers. It works in 3 dimensions too. It's cool. So this is a couple of projects that combined where we've been sampling down by Harts Creek down here, and then we also did sort of transects of multi-level deep wells across Central Plains. And when you plot those ratios with the same sort of colour scale, you can see that the water coming up near Lake Ellesmere is water that was recharged by land surface recharge on the sort of lower plains. Water recharged in the upper plains, which has these green symbols, is going a little bit deeper down, and the blue is coming from much further inland, or possibly from the Rakaia River. It's coming back up at the coast. And then it doesn't always work, because once you go into the very high country, you don't have the distinction between the rain and the rivers anymore, and everything comes out with the same signature. Like Mackenzie, the rainfall is falling at a similar altitude to where the rivers are sourced, so everything's got a very negative signature, and you can't believe it. But in most other places, the Canterbury is very interesting. Why does it matter? Why do we want to know where our groundwater comes from? It matters because of vulnerability. The groundwater that goes through the land surface is much more vulnerable to whatever you do on top of the land surface. And so we see this is that same cross section. This is the rain on the plains, and it's gone through the farmland, and the red is the nitrate concentration, high nitrate. The rain that's come from high country and possibly from alpine rivers, much lower nitrate concentrations. So that's why I think it's useful. Something similar in Christchurch. This is all dominated by Waimakariri river water. Okay, the land use is a little less intensive, but it's also got much less nitrate than down here, where we're starting to see soil drainage being the dominant source of recharge. And these are nitrate sort of heading up to the 5 milligrams per litre as you get further south. And it's one of the factors we used when we were working on nitrate risk maps for the community and public health. So we knew from our monitoring data what sort of trends we had seen, but we also knew that if you have a lot of river recharge, like you do in Christchurch, there's quite a low risk that any well you drill is going to be exceeding the drinking water limit. But if you have land surface recharge, this is the Ashburton Plains, and you've got some sources of nitrate there, you've got quite a high risk that a well, an individual either shallow well, is going to have a nitrate concentration over the drinking water limit. So where does that groundwater come from? Well, it might have come from comets and asteroids or something really cool, but as far as I'm concerned, it comes from rainfall recharge coming from irrigation or rainfall draining through the soil, and it comes from our rivers, and we have some pretty new tools to try and map out where those two are most dominant. That's about it. I saw this on Sandy Bogan's wall. Waterfalls from the sky and this comes downhill. I added the rest. Thank you for listening. I'm allowed to have questions.
Yes.
Sorry about all the Michael diagrams and equations and stuff. It's just so cool.
So I got slightly confused by the low alpine and high alpine delta rating, because is it the low alpine has got a higher or lower, more negative delta rating than the high alpine?
It is complicated. It goes more negative the higher up you go. But there's also the Aurari, which has a more easterly source.
Oh, so that would be what?
That it's got a it's even more negative. Like most of them
Yeah.
are -9, but their RE is -10.
So that
And
would
they
be
think
good.
it's something to do with where the rain comes from, because the rain is coming from the west. So by the time it gets to the top of the Alps, it's got to very negative. But then if it goes over the Alps and carries on going, it
Okay.
runs through a few more cycles. And
Yeah.
by the time it rains at their source of their RE, it's actually even more negative, on this side. So they call it a rain out effect. That's the theory at the moment for why. Because the RE and Ashburton and Ashley, I think, are a little bit more negative than some of the big rivers which come closer to the bottom.
So thinking about the Mackenzie Basin, where you said that they're all pretty much the same sort of value, and thinking about that rain out effect, is it possible that the water in the lakes might have a less negative value than the rain that actually falls on the basin? Like you might sort of see the opposite then. Like on the plains, you'd think that the more negative values come from the rivers and the less negative values come from the rainfall, but might it just be the opposite in the Mackenzie Basin where the less
We've
negative
only got
values.
3 measurements from the lakes. They're all less negative. They were like -9 instead of -11 or 12, obviously, in the groundwater. It's quite hard with lakes because you can evaporate from the surface of the lakes, so you can change the salinity there. So surface water people are a bit nervous about oxygenized once they're underground, they're safe from evaporation, but if they're just in the water body on the surface, then they can change. Could be right. But there's also the complication that those lakes go through hydro turbines. Depending on where you sample, I think these were sampled from the outlands. I'm not sure. I wasn't going to put more modern confidence in trying to interpret those 3 data points that we do have, but they're interesting. One wants to go sample. One wants to go sample Mackenzie Lakes.
In traces, one of the things that I find challenging, and I'm interested in how you deal with it, is there's often 2 explanations for what you're looking at. So if you look at those your triangular diagrams, you've got age and you've got source.
Yeah,
so
different
there's kind of
sources.
2
Yeah.
things that could be influencing it. And I mean, you said about surface water being nervous on isotopes. Sometimes you see isotopes used for looking at, I mean, one particular argument I've been involved in is to do with fog interception and evaporation. And it could be because the water has re-evaporated, or it could be that it came from a very cold source. And so there's often 2 explanations. And how do you deal with that? Because they can be contrary to each other.
And the one thing that I did get out of all that isotope stuff is just don't try and do them in isolation. I would like collect the chemistry as well, make sure everything's telling the same story, because we can't get 2 or 3 different stories, and you usually latch onto the first one you think of.
Yeah.
So no, I just enjoy. I don't really know the answer to it. Sorry. Yeah.
Well, it's true though. That's a good example of that Rangitata Plains one where the two things
tell the
confirm
same
each
story.
other.
Yeah. So that helps. Yeah, and also like don't forget all the physical, the quantity stuff as well. Try and link your whole story together. You can tell a very big story with 2 measurements if you know what story is you want to tell at the beginning.
Lisa, I was interested to see that the water on Banks Peninsula was totally different than the water in the main alpine streams. I've done quite a bit of work around Banks Peninsula, and the farmers there all believe that when the Wainakaweri and the Rakaia are flowing high, their springs flow greater, so that there's a connection. And I know that environment Canterbury is all about staying connected. So what's your thought along these lines? What can I tell them?
It doesn't
Ring Lisa.
look like a physical connection. You do also get like with recharge, you do get 2 things. You get the actual volume moving, and you get pressure moving. So you can have water that has a different composition that's moved because of some other water that's pushed it along, if that makes sense. I don't know if that would happen with Banks Peninsula. We don't even have wells on Banks Peninsula. I hardly ever look at it. I had to go looking for very old spring data to find groundwater stuff for Banks Peninsula. So it's interesting.
Ask Keith, it's amazing.
Well, I don't need to, because
I've already done it.
yeah, no, Dave Penny actually sorted it out some years ago where all the groundwater came from.
Yeah.
And for example, we know that the groundwater in the Rangiora area comes from Nelson's.
It goes along those flow lines.
And it does, yeah.
Energy ones. It's going to be a lot more interesting than boring those down wells.
Can I ask a second question
Yes,
then, which is
sure.
kind of linked into what Ken just said? You made a comment when you were showing the cross section, and you had the deep groundwater, and you said something like, yeah, one of the island days, that one's fine.
That one.
Then, yep. And you, for the blue, the deep groundwater, you made a comment of this could have come from our one rivers or elsewhere,
Or very high up the plains. That's the problem, is because
Yeah.
as you start getting to the top of the plains, the difference between your river and your rain is getting smaller and smaller.
But you're still talking about on the plains. You're not talking about sort of a groundwater table in the Alps.
No, I'm talking about like top of the plains, your groundwater signature's getting closer and closer. And this is anything less than -8.9, so -9-ish. Could just be rainfall above a certain altitude. Where's it? I'm going the wrong way. Sorry. Now I've really done it. Rainfall graph. There's so little data, but people have tried to make lots and lots out of it, but it goes down like, which is that? For every so many 100 meters, it drops by this much, so -9 would correspond to an altitude of about 300 meters above sea level. So,
You see on that
and
map,
that's also
up at Hororata, there's,
honestly
we've had lysimeters there they're not active anymore, but we used to sample them for a while, and for a while they were doing oxygen isotope ratios in the soil drainage water with the lysimeter. And the values they were coming up with were pretty similar to the values we've seen from the Waimakiroi River and the Wakaya River. So up there above Hororata, rainfall recharge possibly has quite a similar signature, so it's a bit hard to tell for sure.
yes. So, initially it looks like it's all Alpine River. We'll be a bit careful when your rain is high altitude.
Lisa, let's just say that instead of asking the question, where does groundwater come from, the question was, where does it go to? Would you use the same sort of techniques, or would you have to do that another way?
You would use, in some of those techniques are good, those cross sections are good, they tell you where it's going to, the flow lines tell you which direction it's going, where it ultimately ends up, that's the hard part, and how much goes offshore, and that's also the question we don't really know how to answer. Other than putting it in mass balance models and the missing bit. Yeah. I mean, we know when it's coming the other way. We just need the chemistry from that well at Mikiki to know this water's coming in. But measuring groundwater going up to see what things like already. Do that.
So
Please.
does the rain in Spain fall mainly on
Pretty much. Except when it comes from a river. You got to find the next round and that falls the video.
Probably in Canterbury, more rain falls in the mountains.
Doesn't quite fit in the line,
No, no, the rain in Canterbury falls me in the amount, it just,
No.
no, my fair lady would have died. Thank you very much, Lisa. Yeah, thanks all for coming. So we've got another seminar coming up in about 6 weeks. I don't know, have we booked
Not yet, we haven't.
someone yet? We have talked about possibly even getting external speakers now and again, but we've still got a lot of talent and information in our own group. But yeah, keep an eye on the internet and emails, and an announcement will be coming out soon. But no, thanks very much for coming.